exploring the frontiers of incompleteness, a project that involves bringing renowned thinkers on the foundations of mathematics here to tell us their views about the foundations of mathematics. And it's a pleasure to have Hugh Woodin as our first speaker. His talk is going to touch on a number of themes that appear throughout this. Speculations on the nature of set theoretic truth, a thesis in 4 parts, followed by 4 conjectures.
Thank you. It's a pleasure to be here on the equinox. So I guess that's half light and half dark, half thesis, half conjectures. I'll leave it to you to figure out what's light and dark. Okay, so the first part are just some thesis of principles. The second part will be specific mathematical conjectures, coupled with meta-conjectures. So they'll be precise conjectures. Okay, so I'll begin with a thesis in 4 parts. So I'm going to make a lot of definitions, many of which will be familiar, but just for a complete record, I will make those definitions. So, axioms of ZFC. So, just for the record, here they are. Of course, comprehension is a scheme, that's axiom 5. And then we move on to the more serious axioms, power set, the axiom of choice, replacement, a scheme. And then infinity. Without infinity, I guess we wouldn't be doing anything here. Okay, so those are the axioms. And the reason for listing them is I want to talk about a variation. And the variation is not a standard one. So it's the axioms of finite set theory. So I'll call that ZFC naught. So I'll go a little bit more slowly here. So we have these 5 correspond to the 5 axioms for ZFC with one exception. Axiom 2 in the ZFC list was a pairing axiom. I can't have that axiom anymore, so I replace it by bounding. So bounding simply says there is a set such that every object in my universe is a subset of that set. By extensionality, that set's unique. Okay. Comprehension is the same, regularity is the same. Okay. Now there'll be some changes. Power set, I'm splitting into 2 parts, in part because I don't have pairing. So these are the 2 parts. It's not really important what these say, assuming they do what I want. And then instead of the axiom of infinity, I'm putting in the axiom of finiteness. Okay, so that's finite set theory. And I'll try to make a little clearer what's going on right now. So you're all familiar with the cumulative hierarchy. So that generates all sets in a transfinite iteration of the power set. So you start with nothing and you keep collecting power sets. And at limit stages, you take unions. And it's a consequence of the ZFC axioms, in particular the axiom of regularity, that every set belongs to V alpha. So that's it. That's the universe of sets. All we have to do is understand that, and we've got everything. If only life were that easy. All right. So what do the ZFC axioms do? ZFC naught axioms. You take the ZFC naught axioms 1 to 6. That's without the axiom of finiteness. What you get is that V is V alpha plus 1 for some order. And then you add in the axiom 7, that axiom of finiteness, and you get that alpha is finite. Hence, ZFC naught are the axioms for finite set theory. But the reason I'm saying it this way is you could imagine using axioms 1 through 6 as your real, and put in an infinity axiom or something. So I'd like to claim you could work in V alpha plus 1 as easily as you work in V. Okay, that's the idea. All right. For each finite ordinal, Vn is a model of ZFC naught. Each finite ordinal bigger than 0. V0 is awkward because it's empty. So ZFC naught is a very weak theory. Okay, in fact, it can prove its own consistency. It's an amusing exercise. But it does not prove that there's a model of ZFC naught. V1 is the smallest model of ZFC naught. It has only one object in it, the empty set. But ZFC naught cannot prove that V1 exists as a set because V1 is a model of ZFC naught. So in the argument that ZFC naught proves its own consistency, it's a trade-off between, look at V1. V1 thinks ZFC naught's consistent. There are no proofs. The only object's the empty set. That's not a proof. So once you start having proofs, that forces more and more sets into the universe. And so that's how you do that. The curious thing is that the axioms of the form Vn exist for specific n, like 1, 2, 3, 1,000. These are large cardinal axioms for ZFC naught. Okay. So we're not used to thinking of large cardinal axioms in this setting, but they really are. ZFC naught can do nothing without non-trivial existence principles. Just like I would claim ZFC can't do much in the true theory of the infinite without existence principles beyond ZFC naught. We know those are large cardinal axioms. All right, so that's the setting. So now I'm going to go to the fanatical phase. Let's look at Gödel sentences. So Gödel sentences for ZFC naught. So just as Gödel constructed a Gödel sentence, there is a sentence in the language of set theory with a property indicated. If you take any model of ZFC naught, the sentence is true in the model if and only if the model thinks ZFC naught proves its negation. And that's just a routine Gödel sentence construction. Okay, this sentence is a little too pathological. And the reason is, if you think of my universe as a Vn, there can't be much extent to Vn path. N can't be that much larger, probably plus 3, over where the proof appears. Because then it can build a satisfaction predicate. So if you take any model where of this sentence, there's kind of a ceiling where it sees this proof, but it can't go very far past, otherwise it will build a satisfaction predicate and contradict the ZFC naught axioms. So it's not a very good sentence. You know, if you thought about it, if you encountered that sentence, if you encountered the witness, the proof, as you explored your universe, you know Armageddon's 2 power sets away, or 3 power sets away. So you're not going to find it. So let's change it. So this is the change, phi naught. Now, there are 2 numbers here which you can change at will, the 1,000 and the 10 to the 24. I just chose these for reasons that will become apparent. So phi naught asserts first that Vn exists where n is the size of V sub 1,000. That's the large cardinal axiom. So remember, the size of V sub 1,000 is 2 to the 2 to the 2 to. It's a stack of powers of 2 with 1,000. Then when you do V sub that, this is an enormous set. Okay? So the sentence is saying this large set exists, and then it's saying there's a proof of my negation of relatively small length, at most 10 to the 24th, from not ZFC naught, but ZFC naught together with this large cardinal axiom. Okay, so that's the sentence. Okay? So let's look at this sentence a little bit, because I'm headed toward my first thesis. This is why I chose 10 to the 24th. This sentence, if true, is physically verifiable. Right? It's a string of length 10 to the 24th. You have to check that it's approved, but if you know the string and you had enough computer time, first of all, you could store the string. It's not beyond what you could hope to store physically on Earth in a large enough memory. And then you run enough time, you can check the proof. Maybe you set it up so that the string has nice witnesses to help that computation. So I would claim that phi naught is a meaningful statement about the actual physical universe. It's saying there is a binary string Well, I didn't tell you what proof was, or length of proof, so 10 to the 24th or 10 to the 26th, depending on how you set up the formal logic. There's some binary string with a verifiable property. That is a physical statement, whether or not that exists. Is it true? Is the sentence true? Well, of course not. But we have no evidence that it's not true. And now why is it? Look, if it's true, this series of lectures would focus on a very different problem. If this sentence is true, there is no mathematics, because v sub 1,000 doesn't exist. Not only is the conception of the integers contradictory, you can't even have this one big number. Okay, but what do I mean that we have no physical evidence? Well, you're not going to use v sub 500 to refute the existence of this string. Because if you could, you'd have a proof the string doesn't exist. v sub 500 is vastly more complicated than our universe, at least if you talk to the physicists now. v sub 500 or v sub 50 is probably more complicated. v sub 500 is a huge finite set. You have all the power you need to look at that set because you have v sub 1,000, a much bigger set. So you can't use any structural principles of v sub 500 to deduce the string doesn't exist. Well, what could you do? You could start searching through strings of length 10 to the 24th. And in 2 to the 10 to the 24th steps, you'll have a proof. But you're not going to do that in this universe. All right, so now I want to address another issue. So this is maybe somewhat tangential to my point, but let me do that. Physicists might say, I don't care, it's an irrelevant sentence, because you're never going to find the string. Well, is that really true? Now, if this was a Newtonian world, then whether or not I could find the string through my whatever investigations I hope to undertake is a consequence of the initial conditions of the universe. And it's either true or false. And maybe it's just false. But this is not a Newtonian world. It's a quantum world. We have truly random processes. So, all right, I build in my lab, someone else's lab, I build a device with 10 to the 24th quantum coins. And I flip them all. Now, quantum mechanics says any string has a possibility of being the outcome. One of those could be the Armageddon string. So I can't, as a physicist, say there's no chance that you will encounter this string. The probability is very, very small, granted, but there's some chance. So it is, I therefore claim, a physically meaningful question. Now, maybe in 1,000 years, they'll see that quantum mechanics wasn't quite right, and maybe the physicists of that age will actually build an NP-complete machine. True observational mathematics. Well, then you dial in looking for the string, and you run the NP-complete machine, and if that string exists, it's going to find it. So then the non-existence of the string becomes a verifiable fact in that universe. So again, it's a physically meaningful question. To say that it has no meaning for this world is to say quantum mechanics is flawed, is to say there will never be an NP-complete machine. So I would claim that that's not a viable option. So the only coherent basis at present for the assertion that this sentence is false, that string does not exist, must also yield the conception that v sub n, where n is the size of v sub 1,000, is meaningful. All right, so that brings me to the first thesis. Any coherent basis for the mathematical claim of consistency of a formal theory must be paired ultimately with a conception of mathematical objects with structure whose existence implies the consistency of T. There's just no other basis. Remember, consistency is a pi-0-1 sentence. You're not going to check proofs in finite time to verify consistency. You can refute my Armageddon sentence in a finite search, but you're not going to verify consistency in a finite search. Now, I'm not saying that if the claim of consistency is in a theory that's talking about widgets, that the conception of objects must be of widgets. Maybe it's something else. But this is the only basis for the claim of consistency. Remember, consistency claims are universal statements about the integers. So now I'm kind of moving to a setting where we grant that arithmetic truth is meaningful. So if you're going to not grant that arithmetic truth is meaningful, I think one would have to back up and we debate whether questions about strings of length 10 to the 24th are meaningful. Okay, so that's the first thesis. All right, now I want to do a really quick bit on consistency and independence in the ZFC. I'll make some definitions now, but not need the definitions for what I'm going to say. I just want to give an example, because I'm leading up to my second thesis. Okay, so in set theory, omega-1 is the least uncountable ordinal. It's a set of all countable ordinals. In infinitary combinatorics, two natural objects of study, the closed cofinal subsets of omega-1, omega-1 is an ordered set. And so closed in the ordered topology, the closed sets, at least assuming the axiom of choice, are closed under countable intersections. They define a filter. So the positive copositive set, a positive set is a stationary set, and that's what we're going to be interested in. The sets which are positive and copositive, namely the sets which are stationary and co-stationary, are arguably the simplest manifestation of the axiom of choice. Okay. I'm not going to dwell on that, but it makes them objects of interesting study, because the axiom of choice is controversial, or was in set theory, so maybe we should look at the simplest kinds of sets that we get from the axiom of choice that we seem to need the axiom of choice to construct. And as I've said, those are arguably the stationary co-stationary sets. If you have an omega-1 sequence of distinct reals, you get a stationary co-stationary set. So we have, now let's be mathematicians, how complicated is the structure of this case stationary co-stationary sets? Trying to understand them. Could there exist a small generating family for these sets? How many are there? Okay, so here's a precise question. Could there exist omega-1 many stationary sets, which are disjoint, such that every stationary set contains one of them modulo a non-stationary set? So we want omega-1 many stationary sets that can get inside any stationary set. It's like a basis. And the assertion that S alpha is contained in S modulo a non-stationary set is just the assertion that the difference S alpha take away S is not stationary. So it's analogous to looking at infinite sets of integers modulo finite sets. There's a smallness notion, in this case non-stationary, and we're interested in sets which aren't small modulo small sets. So can there exist omega-1 many stationary sets? And the observation, which is routine, is that if you had such a sequence, it would give in a natural sense a basis for the stationary sets of size omega-1. That's all I'm going to say about stationary sets. Here's a line of investigation that isolates an interesting problem. Okay? And there's some non-intuitive consequences, which it turns out that the existence of such a sequence implies that the continuum hypothesis is false. And the conjecture that's open is that the existence of such a sequence actually implies that the continuum is L2. So I'm just saying that there's some subtle and combinatorics floating in the background. But there's a question, naturally motivated, it was investigated. So this isn't just an ad hoc question. This kind of question was investigated. Okay, so now I'm going to change to a completely different setting. I'm going to isolate two questions in infinitary combinatorics. Second is a more familiar one. It concerns infinite games on omega. For a set theorist, omega, of course, is the non-negative integers. And how is this game? What do? We start with a set of integers A. I'm setting up where I'm viewing the reals having the Euclidean, standard Euclidean space. You can set this up a variety of ways. So given a set of reals, we have a game with two players. What the players are doing is building a function from omega into 0 and 1. They're building an infinite binary sequence, and they're taking turns. So player 1 specifies f of 0, then 2 specifies f1, then 1 responds with f2, and so forth. So they just take turns choosing the values. And then after infinitely many stages, we get our infinite binary sequence, or our function from omega into 0, 1, and then we form that sum from 0 to infinity of f of k to the minus k plus 1, and we ask whether that number is an A. If it is, player 1 wins, otherwise 2 wins. So that number is in the unit interval. This only depends upon A intersect the unit interval. Okay, so that's a game. That's the kind of game I want to look at. The only thing to remember is that it's initiated by a set of reals. Tell you the set of reals, I have to find the game. Okay, what's a strategy? A strategy is a function from the finite binary sequences into 0 and 1. And a player can follow that strategy by applying that strategy to f restricted to k to produce what that player needs to, when that player needs to find f of k, that player just applies the strategy to f restricted to k. So that's following the strategy. You don't think. You just see what's happened. You consult your oracle or your strategy. It gives you a 0 or a 1. That's your next move. It's a winning strategy. If you follow the strategy, no matter how the other player plays, you win. So either player can choose to follow the strategy, but it can't be winning for both players, because if they both follow the strategy, the real produced is either in the set or not. So in the early 60s, Michalski and Steinhaus just formulated an axiom. The axiom of determinacy is the axiom that for all sets of reals, there's a winning strategy for one of the players in the game given by A. An entirely, completely ad hoc axiom. It turns out it contradicts the axiom of choice. So for me, the axiom is false. But now there's an interesting question. Do you need the axiom of choice to construct a counterpart? That's my second problem. So we had the basis problem for the stationary sets. Now we have another problem. And we'll be seeing AD quite a bit. Two problems. Both arose naturally. Well, both arose. Okay, the last thing I want to talk about is large cardinal axioms, and I will call these the modern large cardinal axiom. They use a certain language or a template, and this is it. Kappa is a large cardinal axiom if there exists an ordinal alpha and a transitive set M, and an elementary embedding from V alpha into M, where kappa is the least ordinal that's not sent to itself. Given such an elementary embedding, so an elementary embedding is a map that preserves logical truth. Okay? The crit J, for crit is for critical point, denotes the least ordinal not sent to itself. If there's no critical point, if every ordinal is sent to itself, then J has to be the identity on the alpha. So we're interested in non-trivial embeddings. One can require more sets belong to M, possibly in a way that depends upon J's action on the ordinal. So we get a hierarchy of large cardinal notions by the dials we can turn. If you assume the axiom of choice and you take M to be V alpha, then alpha must either be lambda or lambda plus 1, where lambda is the supremum of that sequence. That's called the critical sequence. Kappa 0 is a critical point. You just iteratively, infinitely many steps, apply J. So those are the large cardinal axiom. Not every large cardinal axiom is of this form. Some are of the form kappa is a large cardinal if there are many embeddings, possibly with critical point less than kappa. But this is the basic module. Elementary embeddings from a rank initial segment of V into a transitive set, and how those relate to kappa are the degrees of freedom in specifying the large cardinal axiom. Okay, so measurable cardinal would just say, many of you may have heard of that, It's just the existence of an embedding with a critical point. Okay, the simplest one. Okay? So we have three theories. Theory one is there are omega-1 many stationary sets that define a basis for the stationary sets. ZF plus AD, that's asking, did you need the axiom of choice to construct a non-determined game on omega? And then we have a large cardinal axiom, which I won't define, just ZFC plus there are infinitely many Woodin cardinals. Okay, now what can we say? It's a theorem, these three theories are equiconsistent. They're talking about completely different objects. The first theory is talking about subsets of omega-1. The second theory is talking about sets of reals in a choiceless context. And the third theory is talking about big cardinals. These are each recursive theories, and they're equiconsistent. That's a number theoretic statement. That means you show me that if the theory 1 is inconsistent, theory 2 is inconsistent, and theory 3 is inconsistent. Okay, so now this brings me to, so this is just an example, and it brings me to my second thesis. The conception of the universe of sets with the structure from large cardinals can account for all possible consistency claims. So remember, thesis 1 was you have to have a conception of object with structures to account for a consistency claim. This is saying this suffices. Okay? It's not saying you have to do it this way. Maybe you want to think about widgets, but that this suffices. So this is a hopelessly vague thesis, but I hope to convince you that in the end it's not so vague. It's reminiscent of Gödel's claim that you could settle all statements using a large cardinal hypothesis. This is not nearly so ambitious. It's just saying you can account for all consistency claims. And the evidence is, here's a non-trivial instance. The consistency claim for Woodin cardinals is giving you the consistency of the other two theories. Okay, that's the second thesis. So now I'm headed toward the third. So I want to mention two large cardinal axioms in ZF. So I'm giving up the axiom of the choice for the moment. These are non-standard large cardinal notions. They weren't traditionally defined. When you do that, you can invent a name. And there's a certain lack of imagination in naming large cardinals. They're strong cardinals, they're compact cardinals, they're super compact cardinals, they're huge cardinals. It's kind of like every time you invented a new cardinal that was bigger, you wanted to say, look, this is really big. So the first cardinal is that of an enormous cardinal. So this is really big. And this is what it says. It's in my template that I gave. It says that you have kappa, lambda, and gamma. You have an elementary embedding from v lambda plus 1 to v lambda plus 1, same rank. Kappa is the critical point. Lambda is the least ordinal bigger than kappa that's sent to itself. There is an ordinal sent to itself. Lambda is, so it's the least. But now there's an interesting wrinkle. We say that v lambda is an elementary substructure of v gamma. So what's going on here? There's some kind of cycling. If you have an elementary embedding from v lambda to v lambda, well, v sub kappa is an elementary substructure of v lambda, just by standard methods. So really the way to think of this is you have v kappa, an elementary substructure of v gamma. Well, all right, the existence of the embedding is seen in v gamma, and that creates complexity, structure. Then that has to reflect below kappa. And then that creates more, so it cycles. And it's some kind of fixed point. Okay, so this is a large cardinal that's near the ceiling of the, well, let me state the second one, and then I'll say what's going on. I'm not going to be so creative with the name for the second one. I'm going to call it a weak Reinhardt cardinal. It's exactly the same statement, except the 1 is replaced by a 2. It's the only change. Okay, so we have these two large cardinals. It's in ZF. We've given up the axiom of choice for the moment. Okay? Woodin showed that if you assume the axiom of choice, you cannot have an elementary embedding from v lambda plus 2 to v lambda plus 2. So there are no weak Reinhardt cardinals if you assume the axiom of choice. So now whether or not we have the axiom of choice is becoming an important issue. Nevertheless, if you assume that you have a weak Reinhardt cardinal in ZF, and that's not known to be inconsistent, it implies the consistency with ZFC, with the axiom of choice, for a proper class of enormous cardinals. Okay. So, is this a suggestion that we're going to have to abandon the axiom of choice if we're going to take thesis part 2 seriously? So let me just say what's going on. It's not known if weak Reinhardt cardinals are inconsistent with ZF. What the second theorem is really asserting is that a weak Reinhardt cardinal in ZF implies all known large cardinals in ZFC are to be consistent. Note, it is stronger than any large cardinal in ZFC that anyone has ever proposed. And there's a persuasive argument from the proof of the second theorem that it's actually stronger than anything you can formulate according to the template that I described. So the possibility is raised that the strongest, most powerful large cardinals have to exist in a universe where the axiom of choice is false. So my conception of objects and structure, I'm going to have to move to a conception of the universe of sets where the axiom of choice is false, if I'm going to take the second thesis seriously. Well, this is a disturbing idea. You know, it's very hard to work without the axiom of choice. That's why it's not known that weak Reinhardt cardinals are inconsistent in ZF. You just can't do anything without the axiom of choice. It's extraordinarily difficult. Okay, so we have the possibility of a large cardinal axiom in ZF that is stronger than all large cardinal axioms in ZFC. There's no way to account for the consistency of that unless you start a conception of the universe of sets without the axiom of choice. Okay, so we want to explore that a little further. Okay, so let's look at choice. We need to go back and start looking at more canonical constructions. So there's the cumulative hierarchy is generated by the power set operation. Let's be a little bit more conservative. So let's bring in the definable power set. So here's one definition. If you have a set X, P def, remember P of X is the power set, all subsets of X. So now we're not going to take all subsets. We're going to regard X as a logical structure and only take the subsets that are definable in that structure from parameters. That's a much more modest thing. If you assume the axiom of choice, P def of X is equal to the power set of X if and only if X is finite. If X is finite, you can define every subset of it. You're allowed to use parameters, so you just list it. So if you take the definition of the cumulative hierarchy, you simply replace the use of the power set with the definable power set, you get Gödel's constructible universe. There's the definition. You just iterate transfinitely the definable power set, taking unions at limit stages. You look at all the sets you get. That's L. It's a transitive class. This definition works in ZF, but L is a model of ZFC. And that was the point. This gives the consistency of the axiom of choice from the consistency of ZF. The continuum hypothesis holds in L. So you also get the consistency of CH, and that's what the whole point of the construction was. Okay. Well, now we have a problem. We might say, oh, well, here's our conception. Maybe we should give up. We should augment the axioms of ZFC with the axiom that V is equal to L. And there's our robust conception of the universe of sets, and that will do everything we want. Well, that would be great, except for Scott's theorem. Assume V equals L, there are no large cardinals. And I have to say modern because I don't regard inaccessible cardinals as large cardinals. But if you take the large cardinals that can be formulated according to that template, none of them can exist in that. So it's kind of unfair. canonical conception of the universe of sets was revealed and then kind of taken away because of the unfortunate fact that it can't have large cardinals. And the theorem that it has no large cardinals is 20 years after the fact. It's not like it just wasn't known. I mean, Scott's theorems are not difficult. It's, I think, one of the fundamental theorems of set theory. It was proved about just a year or two before Cohen's proved. Scott had the consistency, at least for large cardinals, that V is not L. But then it got completely swamped and overshadowed by Cohen's results. Anyway, I mean, Cohen's results are much harder. Okay, now, Gödel also introduced, L is no good for us. We're not going to use L unless we give up large cardinals. So, there's another transitive class that Gödel defined. He did this in the bicentennial lectures in Princeton. He never published it. It's that of Hod. So here's the definition. For each ordinal alpha, Hod alpha plus 1 is the set. Well, there it is. It's all the subsets of V alpha. You require that A is definable in V alpha from just ordinal parameters. And you require that every element of the transitive closure of A is also definable in V alpha from ordinal parameters, where the transitive closure of a set is the smallest transitive set that contains that set as a member. Set's transitive if every element's a subset. It's like an initial segment of the initial sets. So, again, the actual definition isn't going to be relevant. What I'm going to do, I just have to write down the definition. You can't help but notice that the definition of Hod alpha plus 1 is a mixture of the definition of L alpha plus 1 and V alpha plus 1. It's kind of like you're climbing up the V alphas, but at the successor step, you use the L definition. You jump over. So it's some kind of mix. Hod is not canonical. It can change. Hod may not even think that Hod is Hod. If you build L within L, you get L. If you build Hod within Hod, you may or may not get Hod. V might equal Hod. V might not equal Hod. It's just, it's not a robust or deep conception. The only advantage to Hod is it is a model of the axiom of choice, and Hod can be defined in ZF. And that was Gödel's point. This was another consistency proof for the axiom of choice. Hod, I may actually tell you, HOD is hereditarily ordinal definable. And you can see what the ordinal definable is referring to. The hereditarily ordinal definable is that business with a transitive set. So Hod is the class of all sets that belong to Hod alpha plus 1 for some alpha. I want to caution you that in general, Hod alpha plus 1 is not Hod intersect V alpha plus 1. This is true for the finite. Here's a fact. If the existence of a proper class of enormous cardinals is consistent, then the existence is consistent with V is equal to Hod. Okay, so you can have V is equal to Hod and have these enormous cardinals. Okay, so I want to talk a little bit about classes, because I'll be having to refer to them quite a bit. What's a class? There's an issue there. So I only want to talk about definable classes, but I don't want to talk about arbitrary definable classes. We can't do that. So I'll just restrict. So anyway, class is sigma 2 definable if there is a formula phi in the language of set theory so that the class N is simply the set of all A such that for some alpha, V alpha thinks phi is true about A. So you just inspect the V alpha hierarchy, you have your sentence, and you just collect all the sets where that sentence holds about that set in some V alpha. It's a definable class. That's the definition. L is sigma 2 definable. The sequence of V alphas is sigma 2 definable. Hod is sigma 2 definable. So all the classes I've looked at so far fall into this template. I might want to allow parameters. So we'll say a class is sigma 2 definable. I'll put the tilde to indicate the use of parameters. It's exactly the same, except you're allowed one set as a parameter. Okay? So those are the kinds of classes I want to deal with. And now there's no problem with talking about classes. It's a little bit like number theory. You want to talk about the set of prime numbers. Well, you can do that because it's a definable collection. A set of prime numbers is not a number. But you have no problem talking about them. It's the same thing here. All right, so there are two manipulations we might want to do on classes, and I'm going to define them here. If I have a transitive class and a set, transitive, and now the notation here carries a lot of information. N square brackets x is the smallest transitive class containing n. X intersect m is an m, and m is a model of ZF. That's the definition. Now, I'm not requiring that n is a model of ZF. N could be the ordinals. I'm just saying, you give me a transitive class and a set, I can build a new class, n square brackets x. And then the companion definition is n round brackets x. So this is where the notation is carrying a lot of information. It's exactly the same thing, except instead of x intersect m is in m, we say x is in m. So n square brackets x knows among its sets which belong to x. And round brackets x actually knows the set x. So that's the difference. Now, do these fall into my template? They do. If n is sigma 2 definable from parameters, then these two classes are each sigma 2 definable from parameters. And you're going to have to add a parameter in general. The new parameter that you'll add to the parameters you already have would be x itself. Okay, so you give me a transitive class, I can build a ZF transitive class from it, and a ZFC. I can build two transitive classes. They're each sigma 2 definable. So let's go to a specific setting. And it's a theorem that for every transitive set x, if I take Hod square brackets x, that's a generic extension of Hod by Koellner's method. So it's a ZFC model. If I take Hod round brackets x, it's a symmetric generic extension of Hod. This is a remarkable theorem, because what it's saying is that if you're in a ZF model and you don't have the axiom of choice, then V is not Hod. Because if V were Hod, you'd have the axiom of choice by what I said. Axiom of choice holds in Hod. Well, if you don't have the axiom of choice, Hod round bracket V alpha must fail to be an axiom, model the axiom of choice for large enough alpha. Otherwise, you've got the axiom of choice. So and Vopenka's theorem is saying that you got it by Koellner's method. So that the only way to get a consistency proof for the failure of the axiom of choice is to use Koellner's method. Kind of a remarkable fact. All right, this has an interesting corollary. Suppose kappa is a weak Reinhardt cardinal. Then kappa is a weak Reinhardt cardinal in some symmetric generic extension of Hod. Because I choose alpha big enough so that V alpha can authenticate that kappa is a weak Reinhardt cardinal. Therefore, Hod round bracket V alpha will think there's a weak Reinhardt cardinal. So I've created a weak Reinhardt cardinal by a symmetric generic extension. So here's a speculation that we'll see is ultimately naive, but at this point certainly looks good. Perhaps a multiverse conception. Multiverses are very trendy these days. Based on generic extensions could provide a framework for truth which both accounts for the consistency of weak Reinhardt cardinals, avoiding having to abandon the axiom of choice, and avoids having to settle the continuum hypothesis. Those are the two kind of showstoppers for truth in set theory. So we'll retreat a little, maybe, And by giving up the idea of a conception of a universal set, but some kind of multiverse, maybe we can do everything we want. Okay? So, we want to base it on Cohen's method of forcing, and so that leads to the definition of a generic multiverse. This is a perfectly precise definition, the way I've said it. You have a countable transitive set that's a model of ZFC. Cohen's method gives you ways of building extensions and so forth. So the generic multiverse generated by M is the smallest collection of countable transitive sets, models of ZFC, such that if you have any pair, N0, N1, with N1 a generic extension of N0, and either's in the collection, they're both in the collection. So the issue is, am I allowed to write on this? You start with one universe, and you apply Cohen's method to build another universe. Now that universe might come from over here, so you back up, and then you go out, and so forth, finitely many steps. Okay? I'm working with a countable transitive set. This is, well, I'm transitizing a relation. Okay? The relation is, I am a generic extension or a sub-universe of a given model that the given model is a generic extension of. So I'm allowed to go out by forcing. I'm allowed to back up by forcing. I may not get back to where I started. I may not get back to something that's a generic extension of what I started. Then I go out and back. That's the generic multiverse. So the idea is, if forcing is really the problem, and our ambiguity about truth in set theory is the essential ambiguity that we can't resolve is from forcing, well, let's factor forcing out of the equation. So the generic multiverse, that's a meta definition, of course, the generic multiverse with capital G and capital M is the generic multiverse generated by the universe of sets. Now, this is a meta definition, is what do I even mean by it? The idea is you go out to some virtual super universe where V is countable, and you use the definition. Okay? So that's the generic multiverse. So that gives us a view of truth. We'll say a sentence is a generic multiverse truth if it holds in each universe of the generic multiverse. We all know this is getting kind of problematic because where was that generic multiverse formed? This seems kind of silly. Except for a surprising fact. You can reduce truth to V. You don't need the conception of the generic multiverse at all. So here's the theorem. There's a recursive transformation of sentences in the language of set theory giving phi star from phi. So if you take any countable transitive set, M satisfies phi star if and only if N satisfies phi for each universe of the generic multiverse generated by N. So now I'm in V, I don't need the generic multiverse at all. If I want to know whether phi is a truth, I just check the truth of phi star in my universe. I don't need to move outside my universe. I can reduce truth in the generic multiverse uniformly to every universe of the multiverse. Okay, so now the generic multiverse is looking kind of attractive. Notice that the generic multiverse is the generic multiverse generated by any universe in that multiverse. So that's kind of attractive. I'm now going to speed up quite a bit. Okay, now I want to state the resurrection theorem. So this is a theorem from large cardinals, which is a resurrection theorem. So a sigma 2 sentence is of the form, some prescribed sentence holds in some d alpha, a pi 2 sentence is the negation, some prescribed sentence doesn't hold in any d alpha. So CH and its negation are each sigma 2 sentences. CH and its negation are each pi 2 sentences. Resurrection theorem says if you have a proper class of Woodin cardinals, and I said we'd encounter them again, and phi is a sigma 2 sentence true in V, then for each universe of the generic multiverse, phi is true in a generic extension of n. So what's the saying? I'm in V, I've got a sigma 2 sentence. Maybe that sigma 2 sentence is saying there's an enormous cardinal. I now apply Cohen's method, and I collapse that cardinal to be countable. I can do it. Well, that's no longer an enormous cardinal. All I needed was a proper class of Woodins. Those are infinitesimal things. The resurrection theorem says I can take a further generic extension and resurrect the existence of an enormous cardinal. Well, where did it come from? All you had were Woodin cardinals. So it's kind of a surprising fact. So, as a corollary, at least if you restrict to pi 2 sentences, and you have the proper class of Woodin cardinals, testing whether the sentence is a multiverse truth, you only have to look at the generic extensions. You can forget about the generic multiverse. You just say, I'm in V, I want to know whether a pi 2 sentence holds in my generic multiverse. I just look at all my generic extensions, which I can do, because they're all tagged by Boolean algebras that I can see, and I can assess truth in those generic extensions for pi 2 sentences. Okay, so here's an example. Take any sentence, and look at the pi 2 sentences that sentence holds in V omega plus 2, and that sentence fails in V omega plus 2. V omega plus 2 has all sets of reals, so V could be the continuum hypothesis. Suppose that there's a proper class of Woodin cardinals, and neither of these sentences is a generic multiverse truth. Then take any universe of the generic multiverse. There's a generic extension of that universe in which you make psi true, and there's a generic extension of that universe in which you make psi false. That's resurrection. And V omega plus 2 can be replaced by V omega plus 3, V omega plus 10,000, V delta naught plus 1, or delta naught's the least Woodin cardinal, etc. It's anything that you have a sigma 2 definition for. So, if forcing is the reason that CH doesn't have an answer, that's got to apply to all of these sentences as well. So that brings me to the third thesis, which has 2 parts. The conception of pi 2 truth must be at least as strong as that given by the generic multiverse. By that I mean, if a pi 2 sentence is true in the generic multiverse, it must be true. Okay? Part B is said that granting part A, there are only 2 alternatives. Either the generic multiverse conception of truth or Platonism, or set theoretic Platonism. That means every sentence that's of the form I wrote, it has a determinate truth. And the idea is, there's nothing you can have in between because of the standard argument against CH. If you had a sentence that was not a generic multiverse truth of this form, and you're going to declare that it's true, well, it's forcible and its negation is forcible. So why are you saying it's true? Well, one reason you might be saying it's true is you actually have a conception of V, and you have arguments that that sentence is true in V. But if you don't have a conception of V, in other words, your multiverse is a multiverse of one universe, that seems to me incoherent. Okay, so it seems to me these are the 2 possibilities. Now, you could attack part A. Okay. We got 20 minutes, and I've almost made it to the first half. So I apologize. Okay, there's another consequence of the resurrection theorem, and this touches back on the weak Reinhardt cardinal. So suppose you have ZF and a weak Reinhardt cardinal. Suppose Hod has a proper class of Woodins. Now we're going to look at the generic multiverse generated by Hod. If N is a universe in that generic multiverse, then in the symmetric, there's a symmetric extension of N in which there's a weak Reinhardt cardinal. So this does suggest that the generic multiverse conception of truth might be able to account for the consistency with ZF of the existence of weak Reinhardt cardinals. Just touching back on that. All right, so I now want to look at multiverse conception. I'm going to posit 2 laws that a multiverse conception. We're going to be logicians. We don't know what the right notion of truth is, but if we can do nothing else as a logician, we can analyze models for truth, scenarios for truth. So I'm going to posit two laws. This is for a given multiverse. It doesn't have to be the generic multiverse. If you take any universe of the, everything's going to be tagged to the first Woodin cardinal, not because I'm attached to them, but for mathematical reasons. It's actually so for any universe n, we'll use delta naught to denote the least Woodin cardinal of n. And now I'm moving to a setting where I have proper classical orders. For all the reasons, you know, the resurrection theorem and all of that. So just as omega 1 always denotes the first uncountable ordinal, as I move through the generic multiverse, which ordinal that is can change. So it is with delta naught. Delta naught denotes the least Woodin, and as I move through the generic multiverse, that can change. It might get smaller. Okay, unlike omega 1, you're not going to... Well, if you move through the generic multiverse, you can make omega 1 smaller, possibly. But the remarkable thing by resurrection is that you can be in situations where, by passing to a generic extension, you can make delta naught smaller. And that, of course, you can't do for omega 1. So we'll say that a sentence is a multiverse truth of v delta naught plus 1 if in each universe of a multiverse that sentence is true in that universe's computation of v delta naught plus 1. Okay, so we're kind of looking at a fragment of the universe, asking a question of that fragment. That fragment is tagged to the least Woodin cardinal of that universe. So the first multiverse law is that the set of pi2 sentences, which are multiverse truths, is not recursive in the set of multiverse truths of v delta naught plus 1. Okay, so let's look at this. We're trying to understand pi2 sentences, which are much more complicated than any statement about v delta naught plus 1. And all I'm saying is this law is saying that the truths, the pi2 truths, as a set of integers, cannot be recursive in the set of truths of that simple fragment. If the multiverse has only one universe in it, Tarski's undefinability of truth. This must hold. Because in V, the theory of V delta naught plus 1 is definable by a pi2 sentence. So if the universe, if it's a multiverse of 1, this is trivially true. If you look at the multiverse given by all omega models of our base theory, it violates this law. It's not surprising. I said the multiverse of 1. That is surprising. The multiverse of 1 satisfies the first multiverse law. Here's a natural multiverse where the first law fails. Okay, so the intuition for the first multiverse law is, well, wait a minute, if the pi2 sentences are reducible to the truths about this fragment, haven't you just rejected the universe in favor of this fragment? Well, but it is a multiverse after all, and maybe the global structure of V feeds into those fragments throughout. And so I want to introduce a second law. A set of integers, or a subset of V omega, is definable in this fixed fragment across the multiverse if for each universe of the multiverse, X is logically definable in that fragment without parameters. And that gets us to the second multiverse law. The set of pi2 sentences, which are multiverse truths, is not definable in V delta naught plus 1 across the multiverse. Again, in a multiverse of 1, this is another Tarski's undefinability of truth. So the idea with these laws is we're focusing on a fixed fragment. First law is saying the truths of that fragment have to be simpler than the pi2 truths. And we saw an example where that can fail. The second law is saying, well, even if they're of the same complexity, you can't define the more complicated truths in that fragment in every single fragment that you get from the universes of the multiverse. Okay, so it's those two laws. And if we look at the multiverse given by all omega models, it satisfies the second law. First law is violated, the second law is satisfied. A multiverse of one universe satisfies both laws. So here's the fourth thesis. The conception of a multiverse of sets should not violate both laws. Maybe you can violate one, but you're not going to violate them both. Okay? Therefore, if the generic multiverse is to be the basis for truth, the generic multiverse has to satisfy one of these laws. Now, there's really a parameter family of laws. These are indexed by delta, or sigma 2 definitions of delta. Here, I chose the first Woodin cardinal for mathematical reasons I probably won't quite get to. The smaller the choice of delta, the weaker the law, the less constraint on the multiverse. If you take omega plus 2 as your threshold, that's the weakest plausible version, and we'll call those the weak multiverse laws. So V omega plus 2 is just P of R. So if you interpret these laws in that setting, it's saying the truths of P of R, the pi 2 truths, which include the truths of P of R and anything you can imagine, can't be recursive in the truths of P of R. And at the same time, the truths of P of R, whatever, can be definable in P of R throughout the multiverse. And by accident, it might be definable in some, but it just can't be definable everywhere. I should have said and didn't, there's something very subtle going on if you're going to violate the second law. The definition can't be uniform. But wait a minute, it's a definition without parameters. So you have all these structures, the same set is being defined in each. The definition cannot be the same, otherwise you can just run the undefinability of truth. Therefore, it's changing. But that's kind of strange. Anyway, those are the two laws. Okay, those are, that's the end of the daytime. And now our predictions. Maybe, what? Pardon?
How long will it take to tell us whether the theses are true?
To tell what?
Whether the theses are true. That's what the predictions are about.
Well, no, what the predictions are, and I apologize, I didn't speak fast enough. So, predictions are a series of 4 conjectures, but each has to be introduced with some apparatus that are feeding back on the theses. And the real content is the predictions. A thesis is a vague thing. Maybe what I should do is just jump to the last.
You can have till half past.
What?
You can have till half past.
Well, that's very rude. All right, I'll try to go fast. I'll give you a flavor. All right. First thing we need to understand is the logic of the generic multiverse. That's called a megalogic, capital omega. So if you have a pi 2 sentence, it's valid in this logic if it holds in all generic extensions of V. I'm not saying throughout the generic multiverse, just all generic extensions of V. But by the resurrection theorem, this is truth in the generic multiverse. So what's going on, of course, is had I known the thing about the generic multiverse came after omega logic. Okay, so that's, the resurrection theorem tells us this is, you're valid if you're true. Okay? So now what's missing is a notion of proof. Because we want to analyze this generic multiverse conception of truth. We have this, the logical notion, what we need is the proof notion, so that we can analyze it. So what we're going to try to do is attack the last thesis. We're going to try to attack the multiverse laws. Okay? So, sets universally bare. This will be a pleasant interlude for the mathematicians here. It's just if it's continuous pre-images in any topological space, that's the property of bare. In other words, differs from an open set by a meager set. Every Borel set's universally bare. Some simple collection of sets of reals, defined by some abstract property. If you have a proper class of Woodins, these have a very nice property. If you take A and R, go to that L of A and R. Remember I defined that. It's the smallest ZF model containing A and R as an element. That's a model of AD. and every set there is universally bare. So the universally bare sets have strong closure properties. They're all determinate. That's good because determinacy has lots of structure. Okay, so now, given a universally bare set and a countable transitive model, I'm going to say that M is strongly A closed. Think of it as closed under A. If all of its generic extensions see the intersection with M. Okay, so we have M, we have A, we go to a generic extension, M's countable, there are lots of generic extensions. Pick one, take A, intersect the model, it's got to be in the model. Okay? If A is finite, every set is strongly A closed. It's either in or not. I mean, if A intersect M, we have finite set, hence seen. If M is strongly A closed, then of course A intersect M is an M. Don't do anything. That's a legal extension, but it's much stronger than that. Okay. So here's the proof relation. You say that phi is provable, that's a pi2 sentence, if there is a universally bare set such that in any M that's strongly A closed, that M thinks the logical relation holds. So the idea here is, if you see the proof, you think it's true. Okay. But seeing the proof now is being strongly A closed. It turns out the proof relation is invariant across the generic multiverse. Soundness holds. If you're provable, you're true. That's good. And the omega conjecture is the converse. It's the completeness theorem for omega logic. It says that if you're true, you're provable. And that's open. Okay. And the omega conjecture is invariant across the generic multiverse. Not a pi2 sentence, but it is invariant. So if you're going to use the generic multiverse as the basis for arbitrary truth, you can't claim that the omega conjecture is meaningless. So there's the fundamental theorem of omega logic ties this into the definability issues that we're interested in. It says that if you look at the set of valid pi2 sentences and you assume the omega conjecture, then that set is recursive in the truths of V delta 0 plus 1, violate the first multiverse law. And V omega is definable in V delta 0 plus 1, violate the second law. 1 can be improved to V omega plus 1, so 1 you're actually getting a refutation or a violation of the weak first law. There's a conjecture that you violate the weak second law as well. So what's the corollary? If you have a proper class of Woodin cardinals and the omega conjecture holds, then the generic multiverse violates both multiverse laws. So if you're going to accept thesis 4 part B, you go back to a multiverse of 1. A deeper analysis makes the case that for thesis part A, that you can't have a notion of truth. You have to accept the pi2 generic truths, generic multiverse truths. So the omega conjecture says we have to be in a multiverse of 1. Now we need to investigate the omega conjecture. Oh, so I said conjecture. Remember, 4 conjectures. The omega conjecture is a theorem, CFC. That's a perfectly legitimate mathematical conjecture. It has foundational consequences in terms of the multiverse laws. So that's conjecture 1. I want to very quickly, this is going to go too fast, superconducting extendable cardinals. These are modest creatures in the large cardinal zoo. There's the statement of it. It's saying the target is delta. That's what we're looking at. Take anything bigger than delta, you can find things less than delta, and you get that elementary embedding that sends its critical point to delta. So you're at delta, you take an initial segment of the universe above you, you can get it, an embedding from a universe below up to you. That's not the standard definition, that's a theorem due to Magador. Now we're going to shift to the bottom. In other words, instead of being up at the target of the embedding, we're going to be the critical point. So it's the same kind of embedding, but it's from the point of view of the top now, of the bottom now. We want the embeddings to have critical point delta instead of the image of the critical point. That's an extendable cardinal. So these feel related, but extendable cardinals imply the existence of many supercompacts. These are all of complete insignificance relative to an enormous cardinal. An enormous cardinal wouldn't even pay attention to these. They're so much bigger. Okay, now I'm not going to introduce many more definitions. So an extender is a fragment of an elementary embedding. So you have an elementary embedding from v delta plus 1 to m. That's in our template. M contains v alpha plus 1, and crit j is less than alpha. We use j to get a fragment of j. What we do is we apply j to a set in v delta plus 1, and then we cut j of a back to v alpha. Okay, so E is not an elementary embedding in general. It's just a fragment. Okay. We define crit E to the least ordinal not sent to itself, and it's easy to check that if E is the extender of strength alpha derived from J, crit J is crit E. Crit E knows what the critical point was. Okay, so by Scott's theorem, we can't find large cardinals in L, so we need to specify the kinds of classes that we're going to be looking at. We're looking at sigma 2 definable classes, and we're looking at supercompact. And we'll say it's a weak extender model of delta is supercompact if two things happen. Delta is supercompact in N, and this is witnessed by extenders in N that come from extenders in V. So the idea is we're not just interested in a transitive class of the supercompact. We want that supercompact to be authenticated by large cardinals in V. We want a coupling between N and V, and that's the coupling. Or another way to think about it, we have V with all of these extenders. They're witnessing supercompact. We're throwing sets out, casting them out, keep casting them out, and enough extenders survive, or their intersections survive, to still witness supercompactness. Okay, the inner model program is the attempt to build weak extender models for various large cardinal notions. I've just defined it for supercompact, subject to non-triviality requirements, because after all, V is a weak extender model, and the models produced are true generalizations of L. So here's state of the art. Have a proper class of Woodin cardinals. There's a weak extender model for delta as a Woodin cardinal for a proper class of delta. N is in fact contained in Hod. Every set of ordinals is generic over N. 1 through 3 are not so interesting because they may be trivially true. 4 is the non-trivial requirement that when you enlarge N by the reals, you only get universally bare sets. In particular, N cannot contain all the reals, because not every set of reals in N can be universally bare. N's a model of choice. So this is state-of-the-art by modern theory. These are L-like generalizations. I've just abstracted out a feature. The supercompact in 4 is far stronger than necessary to get 4. You need larger cardinals, but some additional hypothesis is necessary. Okay, so now I promised to finish in 9 minutes. Okay. Is that okay? I think the greatest sin is to go over, but since my end time was ambiguous, I view that I'm not going over it. I'm just talking very fast. The Holy Grail in inner model theory was some kind of inner model at the level of supercompact. And it was believed that you just take the current method and program, and you just work really, really hard, and you will reach supercompact. And it turns out that at exactly one supercompact cardinal, something very strange happens. And I'll call it the universality theorem. If N is a weak extender model for delta supercompact, and F is an extender with critical point bigger than delta, and N is closed under F, remember extenders are functions, then the intersection of the extender with N is in N. And you might say, oh, it's that closure under F that's the problem. L is closed under every extender. But F intersect L is never in L, Scott's theorem. So the closure under the extender is not it. So why is this so surprising? To be a weak extender for delta supercompact only talks about extenders whose image of the critical point is delta.
and they're only a very simple kind of extender. And yet suddenly, you're picking up all kinds of other extenders that weren't part of your construction. Okay, so corollary is that if you have a weak extender model for delta supercompact and kappa bigger than delta is an extendable cardinal, then in fact n is a weak extender model for kappa supercompact. That kind of thing never happens in model theory. So in fact, a weak extender model for delta supercompact inherits all large cardinals that you can express in the language of extenders. So this is a complete reversal of what happens. There's no Scott's theorem. Well, but maybe this is all a precursor to there are no inner models for supercompact. I mean, this is all suggesting that n is V. V is a weak extender model for supercompact. V is closed under everything. All right. So one can state the theorem that if you have a proper class of supercompacts and n is a weak extender model for delta supercompact, if you have every set in n of R is universally bare and every bounded subset of delta is generic over n, then n models the omega conjecture. This may be a vacuous theorem. By the universality theorem, you can't really hope to prove that the hypothesis can be satisfied because of the universality. So that's not the conjecture I'm going to make. Conjecture 2, the second prediction, is that if you have an extendable cardinal, then there is a weak extender model for delta supercompact. Every bounded subset of delta is generic over n. N is actually contained in pod, and is sigma 2 definable from delta, and models the omega conjecture. So if conjecture 2 is true, no large cardinal hypothesis can refute the omega conjecture, and that builds the case of the omega conjecture's theorem, but does quite a bit more. All right. Race along. So this conjecture implies no large cardinal hypothesis can refute the omega conjecture. Okay, so we seem to be headed to, we need a universe of one. Building the case that you can't have a generic multiverse. So by the universality theorem, the successful extension of the inner model program to the level of exactly one supercompact cardinal yields an ultimate version of L. Finding the corresponding ultimate version of the axiom D equals L is much harder. Let's curiously even open where we have the inner models. And the trouble is, when you build these models, you're using apparatus from V, and you're throwing that apparatus out. So the model you build doesn't have the apparatus that was used to build it, unlike L. So when you try to axiomatize, I am this model, how do you do it? Can't identify the structures that were used to build it. And this is a genuinely difficult problem and open down in the Mitchell-Steele models. Okay, last definition. If I have a set of reals, theta of L of A and R is the supremum of the ordinals onto which you can map the reals, some analog of C+, the successor to the L, not from the point of view of L of A and R. Pod, L of A and R denotes pod as defined in L of A and R. There's a theorem that connects determinacy with Woodin cardinals in the purely abstract sense. If you have a proper class of Woodin cardinals and A is universally bare, then the theta of L of A and R is a Woodin cardinal in the pod of L of A and R. Kind of a strange theorem. So, remember we wanted the axiom for V is equal to ultimate L. We don't even know how to build this model. And I've said that in the cases where we know how to build these generalizations, finding the axiom is very difficult and an open question. So I'm going to turn it around. I'm going to state what the axiom is without knowing how to build the model. Here's the axiom. So that's a meta-conjecture. This is not conjecture 3. The axiom for V is ultimate L. Proper class of Woodins for every sigma 3 sentence. And I define what a sigma 3 sentence is. If it holds in V, then you can reflect it into the HOD of the L of A and R of a universally bare set. But you have to cut that model at its theta. So remember, the L of A and R models are models of AD. They're models with rich structure. Therefore, their HODs have rich structure. And this axiom is just saying, have the sigma 3 sentence true in V, it must be true in one of these models. So there is a specific axiom. What are some consequences? axiom settles all questions known to be independent by Cohen's method. I'll give you 3. So now I'm doing V is equal to ultimate L. I told you what that is. The continuum hypothesis holds. The omega conjecture holds. The third is more interesting. It says that V must be the minimum universe of its generic multiverse. But wait, if you have a minimum universe of the generic multiverse, that's a completely different argument to reject the generic multiverse, because it's just truth in that minimum universe. Now, L is the minimum universe of its generic multiverse, and one might think that theorem 3 is an artifact of any L-like construction. If you have a Mitchell-Steele extender model in which there is a Woodin cardinal, it is not the minimum universe of its generic multiverse, even if you restrict to Mitchell-Steele extender models in that multiverse. So now something very strange is happening. That the models you get by the Mitchell-Steele construction, this minimality fails. And yet, for this ultimate axiom, it's just a theorem that it is the minimum universe. So these cannot be Mitchell-Steele-like models. So here's the third conjecture. It's just the second conjecture where we augment, instead of saying n models the omega conjecture, we say n models the axiom V is ultimate L. It's the only change. Precise conjecture. If this conjecture is provable, then in ZF there are no weak Reinhardt cardinals. And we eliminate that whole problem. In fact, if this conjecture is provable, then all the choiceless large cardinals which are known to have such, wipes out the whole choiceless hierarchy. So that whole foundational issue is taken care of. I said end now, and I will, so I'm not going to talk about conjecture 4. The slides will be available, and I invite you to read the last, well, there. We'll have a few more slides. Anyway, so I apologize. I should have paid more attention to time. But what I guess in the last minute, 30 seconds, I really think the subject's at a tipping point. There are 4 conjectures here. I think that if these conjectures are true, there's a very powerful case for an extension of the ZFC axioms that gives as robust a conception of the universe of sets as the piano axioms give for the integers. There'll be no independence by Cohen's method. There'll be no independence except